Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, I would like to do a couple more examples from Chapter 5.3, looking at eigenvalues and eigenvectors. And I'd like to jump to page 27 in your guided lecture notes and look at the transformation T that maps R2 onto R2 defined by this matrix. Now, while it is not obvious to us at this point, in this example, we're going to see what happens when your eigenvalues and your eigenvectors are complex or have imaginary components. But nothing by what I look at initially tells me that that's going to happen. But it is something that we're going to expect to see in this example. Let's get started. Let's first look for our eigenvectors. Sorry, not our eigenvectors, our eigenvalues that's associated with this transformation. Recall, to find our eigenvalues, we look at the determinant of a minus lambda I, and this equals 0. We call this as 0, the scalar. And a minus lambda I always subtracts lambda off the main diagonal. So 6 minus lambda, negative 1, 5, 4 minus lambda. And for a 2 by 2 matrix, we use the fact that the determinant is going to be the product of the main diagonal minus the product of the off diagonal. Notice that this is going to be 6 minus lambda times 4 minus lambda minus a negative 5. And if we multiply this out, I think we get 24. This would be minus 6 lambda minus 4 lambda is going to be minus 10 lambda plus lambda squared plus 5 equals 0. And if we combine like terms and rewrite this in descending order, I believe this is going to look like lambda squared minus 10 lambda plus 29 equals 0. Now we're looking for the solutions to this equation, and it happens to not be factorable. So we choose to use the quadratic formula. So notice here that the quadratic formula will give you lambda, the opposite of b, so 10, plus or minus the square root of b squared. And when you square negative 10, you'll get positive 100, minus 4 times the product of a and c, which is 29, all over 2a, or just 2. Looking at our discriminant, notice that 4 times 29 is negative 116. So 100 minus 116, this will give us 10 plus or minus the square root of negative 16 all over 2. But the square root of negative 16 will give us a complex number for I all over 2. Now, a common mistake that students make is by only simplifying by canceling the 2 and the 10. But remember, you have to simplify all of these terms. You should get 5 plus or minus 2i. And notice that there are two eigenvalues here. There's 5 plus 2i and 5 minus 2i. But they will be always complex conjugates of each other. These are our eigenvalues associated with this transformation. Now let's go and look for our eigenvectors. To find our eigenvectors, we look at the equation a minus lambda I times some vector x is the 0 vector. We have to do this for our complex eigenvalue, and I'm going to choose to use the eigenvalue 5 plus 2i first. Now remember, when you have your eigenvalue, you always subtract it off of the main diagonal only. So look at this matrix. We're just subtracting off a complex number this time. So I'm going to use 6 minus, and I cannot emphasize enough that you should use parentheses here. So to emphasize that, I'm going to put them in a different color. Five plus 2i. And then I'm going to close that parenthesis off. And the reasoning is, as I see more times than I think we should admit, some students just forget that we must distribute the negative into these parentheses when we simplify. That is missed a lot, more times than I wish I would see. Then it would be -1, 5, and then 4 minus 5 plus 2i. And again, I really want to emphasize the use of these parentheses. So it would be this matrix A minus lambda I times some vector x, which has an x and a y component. And this will give us back the 0 vector. And I'm going to simplify that matrix A minus lambda I by distributing those negative signs, those minuses. So I think we're going to get 6 minus 5 is 1. Distribute the negative. This gives us minus 2i. -1. 5. 4 minus 5 is -1 minus 2i. And we're looking now for a vector with components x, y that when you multiply it by this matrix, you get the 0 vector back. And as we did it before, the easiest way to probably visualize this is to write this as a linear combination. So x times that first column plus y times that second column. And generally when doing this, it's easier to look at just one of the rows in this equation. So I'm going to focus on just this first row and identify what would x and y have to be so that this becomes 0. Or specifically, I'm looking at x times 1 minus 2i minus y equals 0. Here, what I'm going to do is I'm going to let x be a value. Like, for example, what if x is 1? If x is 1, then this equation reduces down to 1 minus 2i minus y equals 0, which is going to give y is equal to just 1 minus 2i. This gives us our vector x is the vector with a first component x that's 1 and a second component that's 1 minus 2i. And I'd like to acknowledge that this is a perfect stopping place for your eigenvector that's associated with our first eigenvalue. However, what we're going to see later on in chapter 6 is that they're going to have us rewrite this eigenvector. So I'm going to do it now just for practice, so we'll see it again. Another way to write this eigenvector is the sum of two vectors, one vector containing the real components of it, and a second vector containing the imaginary components. Notice that the imaginary component of the first entry is 0, and the second one would be -2. Notice if you multiply the I into this second vector and add these together, you'll get back the same original vector that we had. However, this is something that we'll be having us do in chapter 6, is breaking up this vector as a real and a complex part. So this is what your eigenvector looks like for your first eigenvalue. We need to find the second eigenvector still. So let's do that on the next page. And maybe this is something I can give you a moment to work on your own. We want to find the eigenvector associated with your second eigenvalue, which was 5 minus 2i. So this is where I'm going to pause the video, or ask you to pause the video, and look for your eigenvector associated with this eigenvalue. So I'll see you back here in a moment. Okay, I hope you pause your video. Let's see how this goes. To find your eigenvector, recall you always look at what happens when you subtract this eigenvalue off your main diagonal. So this will be 6 minus 5 minus 2i. And I really need to emphasize that you use parentheses to avoid sign errors here. Then it'd be -1, 5, and 4 minus 5 minus 2i. But again, if you're not writing this parentheses, I'm a little bit nervous. And we want to multiply this by some vector x to get the 0 vector. And now let's simplify. Remember to distribute this minus sign to each of the terms in the parentheses. This is the part that lots of students miss. I think we get 1 plus 2i, -1, 5, -1 plus 2i, times some vector with components x, y, and this has to equal the 0 vector. And I find it easiest if we write this as a linear combination of those columns of the matrix A. So x times the first column plus y times the second column. And even then, I still find it easier just to focus on one row of this product. Whatever this row is, it has to equal 0 for appropriate choices of x and y. So I'm going to say, well, if we focus on just this one row, then maybe we can more easily determine what x and y have to be. And I'll do this by choosing to let x equal 1. If x equals 1, then this gives us the equation 1 minus 2i or no, 1 plus 2i minus y equals 0, or that y is equal to 1 plus 2i. And this gives us the eigenvector x, that is 1 and 1 plus 2i. Remember, this is only one of the infinite numbers of eigenvectors that'll work. We got this one by letting x equal 1. We could have let x be a different value, and we would have got a different eigenvector, but it would have been a multiple of this one. Now again, this is a fine place to stop for your homework in chapter 5.3. Or identify that in our chapter 6 we're going to go a little further, and we're going to write this vector as the sum of two vectors. One vector that has the real components and a second vector that has the imaginary components. Notice if you add these two vectors together, you're still at your original matrix or your original vector. But they're going to write it in chapter 6 as the vectors 1, 1, and then I times the vector 0, 2. You do not need to write it this way in chapter 5.3, but I'm doing it just so that we'll recognize this step when we get to chapter 6. Either of these could be used for your eigenvectors for this transformation. Okay. I'm going to stop this video here. There's one more example I want to do on your guided lecture notes that has transformations from R3 to R3. But I'm going to do that in a separate video. So I'll see you then.